Welcome everyone to the Introduction to Neural Network workshop given by Daniel Nissani. I am Wedad Anbtawi, the organizer of this workshop on behalf of FruitPunch AI and YATS. So Daniel.
Hey everyone, I'm Daniel Nissani. Like Wedad said, I am a data scientist at Cigna right now, a large healthcare company. I studied at Cornell Tech, where I studied software engineering, data science, business design, just a plethora of different things, but with a focus on data science. I'm not an expert in anything. I don't think of myself that way, but I do have enough knowledge that I can pretend to be an expert when I need to be. This workshop will be me just trying to give you a really, really high level introduction to neural networks. But after this, you should have enough of the jargon and terminology and understanding to go and learn more on your own accord. So I want to talk about how everything's going to be organized for today. We're going to talk about why would we even think about neural networks as being something that should happen. We're going to talk about what is a neural network. So I'm going to try and motivate a very simplistic view of a neural network, so it'll give you a good grounded understanding of what it might be. We're then going to discuss how neural networks work. This will go into the nuts and bolts of how they really work, how they really make strides, and how they build on their performance. And then we're going to go over why neural networks work. I remember when I first learned about neural networks, this was something that was put into a reading for me that I just had to read on my own. I think it's a really powerful result that shows why people even gravitate toward neural networks as a solution. Then we're going to go through different neural network architectures that we have in scope right now. We're just going to go over a couple. There are dozens and dozens of them, some more popular right now than others due to performance increases. But I'm going to go through the basic ones that you'll see talked about everywhere just because of their fame. Then we're going to go over some limitations of neural networks. I don't want you going away from this talk thinking that you can just hit everything with the neural network and everything will be okay. So we're going to go over some limitations that you should consider before using a neural network. And then something that I've never had in a class, and I always wish, was just a what we didn't talk about section. So I'm going to talk about what topics you might want to consider looking into after we're done with this talk. And then some resources. I want to emphasize that the resources and the slide deck are going to be shared after this talk. So if you are taking notes or anything like that, do not feel like you have to write everything down as we're going, as I might go quickly through some slides as they might be just for illustrative purposes. Cool. Any questions before I move on from here? Don't see any in the chat, so I'll just move forward. Just some housekeeping. Some prerequisites for the talk. You should know some calculus. Really, you should just remember what a derivative is. But if you know if you have some calculus knowledge, that will be helpful. You should know some linear algebra. Really, no more than matrix multiplication. But if you want to dive into learning more about neural networks past this talk, I highly recommend you bone up on your calculus and linear algebra skills, because what I hope you go away from this talk, what I hope you take away from this talk is that really those are the core pieces to understanding and innovating in the neural network space. If you understand these two topics, you will be able to understand neural networks well and be able to move forward in your studies very well. This presentation will be primarily visual. So for those who are have math anxiety or anything like that, I'm going to show very little mathematics and I'm going to show more visually what's going on. I'm going to try my best to explain everything that's going on whenever mathematical notation is introduced, but I'm hoping that we can just talk about this in a high level, get all of the concepts out visually. Just like Wedad said in the chat, feel free to ask questions at any time. I know you'll be muted the entire time, I enjoy conversations more than presentations. So if you want to put a question in the chat, Wedad will stop me if I don't see it. And if I see it, I'll stop and address it whenever I can. And then, just like I said before, resources in the slide deck will be emailed. Again, any questions before we get into the weeds? All right, fantastic. So let's keep moving forward. So how do people think up neural networks? So I'm showing this image for a couple of reasons. One, it looks like a bunch of things firing and they're going from one end to another. The way you can think about this is that all those little dots that are firing off and connecting to each other, think of each of the dots as a neuron in your brain, and think of the connections between them are the neurons connecting and firing to each other when they're trying to get an action or a result. So in this case, this is a very famous classification challenge called the MNIST digit. What it is it takes handwritten digits and it classifies whether that digit is a 0 through a 9. And it's a very classic challenge, and like all data science challenges that are ubiquitous in the space, it's always good to get baselines. You do not need to use a neural network for this, but neural networks have shown that they can do this very, very well. And this is a visual of how that might work in a neural network. And we're gonna go through how everything in there is working so that you can have an understanding by the end of this talk. So what is a neural network? Just very simply, what is it? I'm gonna start with a really brief detour, and we're just gonna talk about linear regression. Just to give a preamble, a linear regression is just trying to find a line that is gonna best fit the data set. So notice that this line is trying to fit that data set. It's going through a bunch of iterations, which we're going to talk about in a sec, as to where that line will best fit. And as it gets closer and closer to the end, it's a better and better fit, so it needs less perturbation to get there. So how can we think about a linear regression? So the equation for a linear regression, I have X. Think of X as a matrix of data points, and each data point has like a bunch of features. And you can think of the features as a column in that matrix and a data point as a row in that matrix. The weight, W, is just a vector of different values, and each of those are going to weight the features within each of those data points. The bias term is just some bias that may be in the data set and may not be. It's just something we want to learn because it might not be a completely linear transformation. It might be something that's more affine. So we want to learn this bias term so that we know how much to shift our results to make sure everything works out. If you haven't seen linear regression this way, it's completely fine. I just want to introduce this as one way of thinking about linear regression. Now, why are we going through this iteration piece? Well, we need to learn the parameters W and B, the weight and the bias, because we don't know those a priori. We need to learn what those are. So one way of learning that is you give a cost function. For linear regression, often we give ordinary least squares, such as the cost function presented on the screen. Although there's a closed form solution to solve this, you won't always have that in neural networks. And so what I'm showing here is another way of doing this is something called mini batch gradient descent. So what mini batch gradient descent does is you take the derivative of this cost function, and instead of evaluating the derivative at each data point as it comes in, evaluate it on a bunch of data points at one time. So take a random sample of your data, evaluate the derivative at each of those data points, take the average of that gradient and then go in the negative direction of that gradient. So you're always gonna go negative, and you're gonna keep on going until you find a local minimum, which we hope is the global minimum. In this case of OLS, it is going to be a global minimum that will then optimize the line of best fit. And as you can see in the graph, as you keep on going down that curve, that little dot on that curve, you get a better and better approximation for the line of best fit until it stops perturbing after several what they call epochs, which just means iterations. So why am I even talking about linear regression at all? It's because a linear regression is a neural network. Take that in a bit. Linear regression is a neural network. This is the way neural networks are usually shown. We have our nodes for our input layer. These are what we would call nodes. The way we want to translate that from the linear regression example is these are the input data points from the matrix. So you can think of these as the rows of the matrix that are going in, and they're going to be going to this classification, which is our output. That was the Y in that equation. And you can think of these lines as encoding our W and B. These are like the parameters that are allowing us to go to this point. This diagram is how neural networks are usually shown. And I want to emphasize that we'll have like these things called layers. The layers are what contains nodes. Although it seems like this has 2 layers, we usually ignore the input layer. We don't really talk about that as a layer. So this is a 1-layer network. And the layer is just the output layer with 1 node. What I really want to emphasize from this is that these are the same thing. For me, this diagram is extremely confusing. I can never understand these neural network diagrams. I enjoy these types of mathematical equations that help me understand exactly what's going on, what exactly the parameters are, etc. You will see both in varying different forms. Sometimes you'll see them combined together, but at the end of the day, the big thing to take away from this detour is that a neural network is a matrix multiplication with some added bias. That's it. There are other things that make neural networks better and make neural networks nonlinear and allow them to learn more complex things. But at the end of the day, the real essence of a neural network is some matrix multiplication with some bias. And we're just trying to figure out what those parameters are. Any questions at this point? Feel free to share in the chat. Cool. Again, ask questions whenever you need. I'm happy to see there are none. I can't see your faces while I do this, so I can't judge whether how things are going, but I'm hoping everyone's on the same page for this, because now we're going to get into a little bit harder stuff. So how does a neural network work? This is going to be a section that talks about the nuts and bolts of a neural network. And I'm going to try my best to illuminate these topics to the best of my ability so it's fairly understandable. So I'm going to start with this example. We have E is equal to A plus B times B plus 1. And I want to decompose this a bit. I'm going to decompose it by just having a single operation account for a node within this graph. So I'm going to decompose it so that C is equal to A plus B, D is equal to B plus 1, and E is equal to C times D. Now I'm going to make a graph out of this. We're going to call this a computation graph. And as you can see, A and B are going to go to C equals A plus B, and the operation here is plus. Here, we're going to just go straight to D from B, and all we're going to do is add some constant term, but really the addition is the operation. And then once we have these two, the operation is multiplication. We're just going to go C and D to E. And this is what's known as a computation graph. Why would we even care about this example or think about this for neural networks? Neural networks operate on a computation graph. Matrix multiplication is an operation. So one way we might want to think about neural networks is in these nodes, putting in our inputs, and then at each layer, we're doing a different, or at each moment, we're doing a different operation. And that will be a convenient way of thinking about neural networks when we're talking about updating a neural network, which we're going to talk about right now. I do want to emphasize that these are not the same diagrams. These are describing different things altogether. The computation graph is the underlying infrastructure for a neural network. It's kind of the behind the scenes, almost black box type thing that a lot of frameworks are doing. They're not things you necessarily are ever going to have to organize yourself, but it's good to know that this is going on in the background. This over here is a pictorial representation of what a neural network is. in its entirety and does not necessarily represent the computation graph that's going on underneath. So I just want to make sure those are not the same object. They're different representations that are describing different things about a neural network. So let's just go through a quick example. So if I plugged in A equals 2, B equals 1, C equals A plus B, so I get 3, D equals B plus 1, so I get 2, and then 2 times 3 is going to be 6. This is the most computation that I'm going to do here, because now we're going to talk about why we even care about these computation graphs. So now I want to look at like taking the derivative of each of these nodes, because this is what we're going to do when we try and update a neural network. We're going to have to try and take derivatives, just like we talked about with the linear regression, taking the derivative of its cost function. This is where the really important meat of everything is going in. So one way to do differentiation is the normal way that you all probably learned about differentiation. Look at the inputs to the function. So we can think of E as a function here, and it's really a function of A and of B. So this is taking the derivative of the computation graph, going the forward way. And the first derivative we're going to take is in terms of B. So with respect to the input variable B, we're just going to take the derivative the whole way up. But notice that that only takes care of one input variable. It doesn't take care of the input variable A. So we'd have to do another differentiation in order to get the full derivative of this computation graph. But the other way to take a derivative, and this might not be something that you learned in your calculus classes or anything like that, but it's just important to get the idea, is that we might want to take the derivative just with respect to the function in terms of all of its inputs. So the way that we can do that is we have this partial derivative for E. So we have E as our function. We're just going to take it in terms of E, and then we're going to go and perturb that the whole way through. So then we get for each input, even though these are not necessarily inputs, they're important because of the chain rule, if you remember that from calculus. These are all going to be things that we're going to want to take derivatives of eventually, and we do get the derivatives of the inputs eventually, which is the important thing that we want. Now, why is this important? So in when you're taking the derivative, and if you need to take it a bunch of times, the time complexity for that will get really large really fast. Imagine if we had millions of inputs, which is usually what it takes for a neural network. Imagine we had millions of them. Then we'd have to take millions of derivatives. What reverse differentiation does, if we only have one output value, and usually you have more than that, maybe let's say 10, but then we just have to take 10 derivatives instead of millions. So the speed increase that you get here, it's a huge breakthrough in terms of the ability to implement a neural network when you're coding. This is formally known as backpropagation, and I wish I had the ability to explain backpropagation in a very succinct way, but I don't. But what I do know is that there's a great resource online that I'm going to share with you after the talk called 3 Blue 1 Brown, who's done a very intuitive series on neural networks, who does a great job describing backprop. So I'm going to show that video. And we're just going to look at the first, we're going to look at like about 6 minutes of this video. So I'm just going to go to the mark that I want to go to. Here. About here.
Because the cost function involves averaging a certain cost per example over all the tens of thousands of training examples, the way that we adjust the weights and biases for a single gradient descent step also depends on every single example. Or rather, in principle it should, but for computational efficiency, we're going to do a little trick later to keep you from needing to hit every single example for every single step. In either case, right now, all we're going to do is focus our attention on one single example, this image of a 2. What effect should this one training example have on how the weights and biases get adjusted? Let's say we're at a point where the network is not well trained yet, so the activations in the output are going to look pretty random, maybe something like 0.5, 0.8, 0.2, on and on. Now we can't directly change those activations. We only have influence on the weights and biases. But it is helpful to keep track of which adjustments we wish should take place to that output layer. And since we want it to classify the image as a 2, we want that third value to get nudged up, while all of the others get nudged down. Moreover, the sizes of these nudges should be proportional to how far away each current value is from its target value. For example, the increase to that number 2 neuron's activation is in a sense more important than the decrease to the number 8 neuron, which is already pretty close to where it should be. So zooming in further, let's focus just on this one neuron, the one whose activation we wish to increase. Remember, that activation is defined as a certain weighted sum of all of the activations in the previous layer, plus a bias, which is all then plugged into something like the sigmoid squishification function, or a ReLU. So there are 3 different avenues that can team up together to help increase that activation. You can increase the bias, you can increase the weights, and you can change the activations from the previous layer. Focusing just on how the weights should be adjusted, notice how the weights actually have differing levels of influence. The connections with the brightest neurons from the preceding layer have the biggest effect, since those weights are multiplied by larger activation values. So if you were to increase one of those weights, it actually has a stronger influence on the ultimate cost function than increasing the weights of connections with dimmer neurons, at least as far as this one training example is concerned. Remember, when we talk about gradient descent, we don't just care about whether each component should get nudged up or down. We care about which ones give you the most bang for your buck. This, by the way, is at least somewhat reminiscent of a theory in neuroscience for how biological networks of neurons learn, Hebbian theory, often summed up in the phrase, neurons that fire together, wire together. Here, the biggest increases to weights, the biggest strengthening of connections, happens between neurons which are the most active and the ones which we wish to become more active. In a sense, the neurons that are firing while seeing a 2 get more strongly linked to those firing when thinking about a 2. To be clear, I really am not in a position to make statements one way or another about whether artificial networks of neurons behave anything like biological brains, and this fires together, wire together idea comes with a couple meaningful asterisks. But taken as a very loose analogy, I do find it interesting to note. Anyway, the third way that we can help increase this neuron's activation is by changing all the activations in the previous layer. Namely, if everything connected to that digit 2 neuron with a positive weight got brighter, and if everything connected with a negative weight got dimmer, then that digit 2 neuron would become more active. And similar to the weight changes, you're going to get the most bang for your buck by seeking changes that are proportional to the size of the corresponding weights. Now, of course, we cannot directly influence those activations. We only have control over the weights and biases. But just as with the last layer, it's helpful to just keep a note of what those desired changes are. But keep in mind, zooming out one step here, this is only what that digit 2 output neuron wants. Remember, we also want all of the other neurons in the last layer to become less active. And each of those other output neurons has its own thoughts about what should happen to that second to last layer. So the desire of this digit 2 neuron is added together with the desires of all the other output neurons for what should happen to this second to last layer. Again, in proportion to the corresponding weights and in proportion to how much each of those neurons needs to change. This right here is where the idea of propagating backwards comes in. By adding together all these desired effects, you basically get a list of nudges that you want to happen to the second to last layer. And once you have those, you can recursively apply the same process to the relevant weights and biases that determine those values, repeating the same process I just walked through and moving backwards through the network. And zooming out a bit further, remember that this is all just how a single training example wishes to nudge each one of those weights and biases. If we only listened to what that 2 wanted, the network would ultimately be incentivized just to classify all images as a 2. So what you do is you go through this same backprop routine for every other training example, recording how each of them would like to change the weights and the biases. And you average together those desired changes. This collection here of the averaged nudges to each weight and bias is, loosely speaking, the negative gradient of the cost function referenced in the last video. or at least something proportional to it. I say loosely speaking only because I have yet to get quantitatively precise about those nudges. But if you understand...
So, give me one sec. So I highly recommend you go and watch that video and any of his videos that he's done on neural networks. I think they give a great visual take and very high level intuitive take on what neural networks are. I think we're going through a little bit more in depth with a few things, but essentially what I want you to take away from this video is that back propagation routine allows you to get the changes that you want for each training data point and have each layer within your network propagate back all of those changes so you know exactly how those neurons need to fire in order to get to the exact result that you want. Any questions on that before we move forward? I know that was probably a ton of information. Now, I have no way of seeing the chat window anymore. Oh, there we go. Cool. I'll take your silence as we're good to go. So he did talk about something that I do want to address. He talked about something called an activation function or an activation. He called it the sigmoid squishification function, I think, in the video. These are actual things that are used. The reason that they're used is because if everything was like linear regression, then we would only get straight lines out of neural networks, even with their cost functions. So what we want to do instead is we want to be able to add some non-linearity so that we can get different shapes out when we're trying to do our classification. Some famous non-linear functions that will be applied to the different layers within a neural network are the sigmoid, tanh, and ReLU. I want to emphasize that these are not the only activation functions out there. I actually rarely use these anymore, but they are the ones that you will first learn about as you learn about neural networks because they're almost like the workhorses of data science, particularly the sigmoid. The sigmoid is this graph right here. Otherwise known as logistic regression. If you know what logistic regression is, the sigmoid is the underlying function of logistic regression. We have tanh, which is a function that looks a lot like logistic regression. It's kind of inspired, it was inspired by the sigmoid as being another function that might be good. And then ReLU, the inspiration for ReLU is that it's a straight line on the positive side of the x-axis and then 0 on the other side. And there are many variations of ReLU because it actually increases performance quite a bit. The reason for the first two functions is that you might want your activations to be between 0 and 1 because that might give you a sense that it's kind of probabilistic, even if it isn't a real probability distribution. But the biggest reason you want these three types of functions is because of their derivatives. So if we look at their derivatives, they're fairly smooth, aside from ReLU, which we'll get to in a sec. Their derivatives are fairly smooth. We can track their changes quite well. There are some issues with all of these functions in terms of their derivatives. For example, for the sigmoid and tanh, you may get vanishing gradients here. Notice that eventually your derivatives will start being 0 as you go further out, which can happen. And what that'll do is it'll kind of signal to your neural network that changes don't really need to happen, which is not what you want. You want your neural network to always be trying to encode the changes that are happening, and these could be very important things that the functions are losing. So those are some limitations behind these. For ReLU, you have the other way. You're going to get 0 on this axis the whole entire time. We don't need to worry about that. But going the other way, the fact that you're going to get this constant derivative, you might have a blowing up gradient as you're taking sums that'll always be this large, which also might not be what you want. Each of these have their high points and low points. There are new activation functions coming out every year. trying to figure out what's the best way to add nonlinearity to your neural network. There is no right answer. This is an open research question. Empirically, and I think this is the biggest thing, another big thing to take away about neural networks, they are empirically driven. The mathematical theory behind neural networks is not complete, and everything that people are trying, they're just trying. They do not know whether it's going to work, but we have some inclination that it should for the reasons that we're going to talk about in the next topic. Before I go into why do neural networks work, does anyone have any questions? Again, just feel free to put into the chat. Oh, looks like we have one. Okay. Yeah, great. Let me address, so I'm gonna butcher your name. I'm guessing it's, I'm gonna say Josie, but I think it's Hosier. I'm gonna get to your activations functions question in the next part of the talk. I think it'll illuminate it. And if you still have questions, feel free to ask again. In terms of what's the difference between a sigmoid and a tanh. So a sigmoid is, you can think of it as a reciprocal of an exponential function. I'll actually type like a very simplistic, I think this is the right way to think about it. Something like that. It might be a positive x, I forget the exact formulation for a sigmoid, but that you can think about as a sigmoid. Tanh, I don't want to get into the mathematics too much about tanh. If you know anything about hyperbolic trigonometric functions, the closed form of tanh is just a different form. But there is the primary difference, if you want to think qualitatively between these. Tanh has steeper curve lines going toward -1 and 1. So it's not squished between 0 and 1, it's between -1 and 1. And they have a bit of a steeper slope. You can think of almost like a steeper derivative going up to -1 and down to -1. Whereas sigmoid is between 1 and 0, and their derivatives are a bit less. The rate of change as you go is a bit less as you follow along. I'm going to butcher your name too. Ziad, does that answer your question? Just reply in the chat. Awesome, thank you. Any other questions? These were great. Fantastic, cool. So I'm hoping to answer that question about activation functions, like why do we even use them with this part, because I think this is going to be the important thing. So I mentioned this before, but let's say we have this data set, and this is the best decision boundary that you can really get with this data set. How do we get that decision boundary? There are many classical algorithms out there that might be able to do it, but if we want to use something like a neural network, why would we even think that a neural network will be able to learn this decision boundary and be able to get that? It's definitely not linear. I can guarantee you that this is not a closed form function. We can't write this in terms of just some inputs to a function that'll get this out in any type of nice way. Sure, you can come up with some like extreme way where it's very little curves everywhere that really approximates it well. But like, how do we get to this decision boundary for this data set? And that's the primary question that we want to keep in our head for the next few slides, is like, why would we even hope that something like a neural network is going to be able to learn this? So let's take a little bit easier curve just as an illustrative example. So we can think of this as like a visual proof of why we would even think that a neural network could learn. I'm not going to present any of the mathematics behind it, but this is the official name of the theorem. If you want to go and learn about it, I'm going to bring up some textbooks for you to read, and I'm positive that they're going to have some description. Actually, the first time I learned it is going to be in one of the textbooks that I represent, and they have a great walk through the whole entire thing as both a proof and a practical example. But this is going to give a high-level overview of the universal approximation theorem. So here's this curve, and let's say I want to approximate it. Well, something I'm going to borrow from calculus is this idea that I can break it up into tiny rectangles. But I'm not going to really be worried about like the area under the curve or anything like that. I'm going to more worry about like how those rectangles are approximating the actual red curve. And notice that they like do an okay job. It's not perfect by any means, but notice that I'm able to kind of approximate what this looks like using these rectangles. And the same idea from calculus, if I keep on making those rectangles smaller and smaller, and when I say smaller, I mean the width of them smaller and smaller as I keep going on, I get a better and better approximation of the curve. Now, what does this have to do with anything in terms of neural networks? Well, the idea is, let's say I take two sigmoids and I take their difference. I'm taking a difference between the two right now. Well, what I get is something that looks very much like a little rectangle. And the idea is, given these activation functions and the nonlinearity that they allow, it allows me to build these little tiny pieces of what the true decision boundary might be. And you can think of the updating step that Backprop is doing is trying to figure out what is a better and better decision boundary for actually creating that graph. So I hope that answers the previous question as to why, like, what's going on with the activation functions, why do we care? It's because those activation functions allow us to build more complex curves, because if we increment them together in the correct way, we'll be able to build out such complex decision boundaries that we'll be able to actually get a really good best fit. Does that answer the question from before? Just reply in the chat. Cool, great. Awesome. So, and then any questions on the universal approximation theorem? This is like the crux as to why neural networks work. And I highly recommend that if you didn't fully understand the intuition behind this here, to read some of the resources that I'm going to send to get a better idea of what the universal approximation theorem is really saying, because this is extremely important if you're going to understand like even when to apply a neural network to a problem. Cool. Great. So now I want to go through different neural network architectures. I'm going to motivate these a bit as we are talking, and what I hope the way that I'm motivating these examples does is make you think about when you're using like a vanilla neural network, why it might not be working, and what other mathematics or other techniques you can bring in to try and make a neural network better. Because really that's what different neural network architectures are, is just bringing in other techniques to try and make it so they're learning something better about whatever the data point is. So now comes a little bit of an interaction session. So let's say I'm trying to classify the difference, or try and classify like a cat and a dog. Like it's just a binary classifier. I just want to classify when a picture is a dog and a picture is a cat. How would I do that? Like just yell out in the chat, like just type out, like what are some differences that we might hope to see when we are trying to classify a dog or a cat? Like what are some things you would do? Great, size is a really good one. What's another one? Eyes, yep. Yeah, you can tell like the cat eyes are like a little bit different because they have this, it's more like a straight line in there. Mouth shape, 100%, especially if the dog is like smiling. The ears, yeah, there's some differences in the ears. Maybe there's some differences in color. And just as a data scientist, when I'm reading these things, and these are things that as you start getting more familiar with data science and being really critical of your data, you would ask, what if I had a smaller dog than the picture I had of a dog here? What if the color of that dog, the color of my dog actually more resembles this cat? I do have a dog, and it resembles this cat more than it resembles this dog. What if I had there are dogs that have very sticky uppy ears. I know schnauzers sometimes have this. Whenever I go to the dog park, I see them all the time. So what are the reason I ask these questions is because in traditional data science, so if you were doing an image classification task and you built out these features that kind of like measured, maybe you use some type of segmentation software, so you're able to get like an exact measurement of the ears, maybe you got a measurement of the head, maybe you got the colors or something. Does bit depth help? Maybe, I actually don't know. So yeah, you would want a neural network to still identify it using the other features. So exactly. So the question is though, what are those other features? And this is where neural networks get a bit black boxy, but at the same time, it gives you an appreciation for what machines can do. At times, machines are going to be able to tell features that we'll never be able to think of. We can try and think of as many features in terms of our content domain as possible, but sometimes we'll miss something. We're humans, we're fallible. And I'm not saying machines aren't fallible, but we've developed techniques that allow them to pick up on certain patterns that we may not be able to pick up in the moment, just like now. So one way to kind of think about this is we'll use something called a convolution. Now, I'm not going to go into the rigor about what a convolution is. It requires a little bit more than I think this talk should require. But I am going to go through the discrete case where the way you want to think about it is a convolution is going to be this like window that goes over an image, let's say. It also is used in digital signal processing and stuff like that. But let's just stay with the image example. So it goes over an image with some weights attached to it in terms of how we're going to weight everything in the image. And it's just going to try and pick out like the important things within the pixels that might be able to tell us some type of feature in the image. And we can think of like, in terms of the dog and cat, it's not just picking up on the size of the ears or like or differences like that. It's able to pick up on like certain curvatures that might be really common amongst dogs. It might be able to pick up on certain like ways that dogs are standing that might be different than cats. It's going to pick up on very small nuanced things that maybe we have in the back of our head, but for us to both measure and think of might be really hard. And so the convolution is able to try and pick up on those things and create a little bit of a denser, smaller feature set that we can then operate on. Convolutions, you can think of in bigger ways too. Maybe you want to do it in terms of different colors. Maybe you're doing it in RGB instead of in grayscale. And so this, you might want to pick up on certain things in blue and certain things in green and certain things in red, grab those and create some type of output too. And of course, as you can see here, we're getting some bias. But in terms of what the convolution does, we can then apply it to like a neural network. And really what we're doing in the convolution step is feature learning. So we're learning new features that we weren't able to have before. And then we're able to go into a classification that hopefully will do better with our neural network. And these are called convolutional neural networks. They're extremely powerful tools. They're used both in image classification and in terms of digital signal processing, and they're used many other places too that I'm not going to go into now. But the big thing to take away here is that one of the innovations behind neural networks is less about the classification task or regression task, but about the feature learning. It's able to learn features and learn things about what's going on in the data that we might not have been able to discover before. And I'll talk about this limitation later, but then it's up to like, how is it doing that? Why is it picking up on that pattern, etc. But the big thing here is that it's able to learn features that then can be used for a classification or regression task. Any questions about convolutional neural networks? I'm not an expert on these at all, but I can try and answer anything that people might have at this moment. Excellent, cool. So then we have another thing. Oh, I forgot to change the title of this. Ha! I changed the example at the last minute. So ignore the title, how can we discern the meaning of a word in a sentence? It should be like, how can we predict a future data point based on the past? And one of the things that, oh, sure. Yeah, so I'm gonna go back because I just got a question about convolutional neural networks. So the applications, image classification, image segmentation tasks. In digital signal processing, I've done some research where I saw that you can use different versions of a convolutional neural network. It's actually a combination of the next neural network I'm going to talk about and a convolutional neural network to try and take out background noise from speech. There's a lot of research going on in that. I think Facebook came out with a new algorithm on this a few months ago. Really important task, right? Like when especially in today's world where we're in a giant pandemic and most of us are online, if my dog starts barking right now, thankfully he's asleep, we might want his bark to be phased out so you guys don't hear it and it doesn't disturb our conversation. So convolution can be used for that. The big thing to take away from convolution though, anytime that you have some type of, it's really like it's primarily used for images, but anytime you want to try and truncate your feature space into denser space where you might want to grab some things that you're not sure are in there, convolution is a good way to start thinking about it. In order to go into more detail, we'd have to go into a much larger talk about convolutions in terms of how they're used in calculus and in terms of how they are used in something called Fourier analysis, which I think is outside the scope of this. Does that answer your question, Ziad? Great. Any other questions, please feel free to ask whenever. I'm loving the questions and the participation in the chat. Okay, cool. So now we're going to shift our focus. Oh. Is convolution the same as in algebra? Say more. Yes, yeah, there are convolution matrices. So I am not sure in implementation. They probably are using the discrete. Oh, I don't want to get into this too much. Yes, they probably are using it in the matrix sense. When you're doing an implementation, but I am not sure. But yes, if you know convolution from like a linear algebra class, or even from an algebra class where you learned about the, I think it's the cyclic convolution group or something like that. Yes, it would be a very similar, if not the same thing, at least its brother. Yeah, great. Any other questions? These are some great questions. Great, fantastic. So for the third time, going into the next example or the next thing that we might want a neural network to be able to do. Let's say we have some data, and what this data is representing is like we want to know in the next time step what something's going to look like. So we would call this a time series data set. I don't remember whether I think Wedad has already led a workshop or has facilitated a workshop for you all on time series. If you were able to go, that's great. If you weren't, that's okay too. But time series data, the way we want to think about it is that the next data point is dependent on the past data points. And so what we would want from those algorithms when we're trying to think of like the past data points is we want them to be able to remember what happened in the past, so that we can predict the future. And that's a really hard thing for any algorithm to do. There are some classical techniques that try and do it, but right now, neural networks are kind of the cutting edge for this. And the type of neural network that's the cutting edge for this is called an RNN, or recurrent neural network. And what that does is it makes a prediction on a certain input, and it uses that prediction by concatenating to then feed it into a neural network and produce the next one. And then the next input's going to have that encoded for the next output. So another way of looking at it, aside from this GIF, is if we look at it in terms of this way, we have some input that's going to go into our network. It's going to get fed in again, but this time we're going to have this h of t that's going to be applied to it too. In an unrolled way, here's how it would look unrolled. Where are RNNs used? Time series tasks. They're used there quite a bit. It's kind of like if you really want to hit a heavy hammer on it, go use an RNN. Specifically, if you want to look into a very popular RNN architecture called LSTM, I'll type it into the chat. If it's used in autonomous cars, I wouldn't be surprised. Anything that needs to remember the past, an RNN is kind of not the state of the art anymore, but it's definitely something that you want to have in your back pocket as something to use. LSTM stands for long short-term memory networks. They just have different activation functions that optimize things quite a bit. But the big thing to take away from an RNN is that they remember the past. So tasks, time series, anything that involves language. So until just a couple of years ago, RNNs, specifically LSTMs, were the state of the art for learning language and trying to figure out one meaning. They were used for translation tasks. They were used for text summarization. They were used for everything. If you've heard about word vectors, LSTMs do create word vectors, and that's kind of like what is feeding into the hidden units. It's used in so many different ways. If you want to learn maybe not more about RNNs, but in terms of natural language processing and text processing and things like that, I'm going to be doing another talk next week on natural language processing. We'll go more into the state of the art of what's going on in the field, but also give a high level overview of the ideas behind there. But the big thing to take away is RNNs are used for anything that you want to remember the past. So if there's any data in the past that you want to use, this is like a really good high level way of doing it instead of using traditional time series tasks. Any questions about RNNs before I move forward? Great. So moving forward, I want to talk about the limitations behind neural networks. And I really do want to emphasize, before you go and use a neural network, try to use a classical approach. It feels very unsatisfying, but neural networks, although they're extremely powerful, they're very expensive in several ways that you want to think about for your specific use case. So first of all, they're very time complex. I don't think I've ever, maybe when I first started doing things, I was successfully able to train a neural network on a CPU, but I almost always now try and find some type of GPU to use it because GPUs are really good at matrix multiplication as an example. But the time complexity for a neural network, just because of all the updates and computations that it's doing at a time, is extremely high. And so you want to make sure that you're finding that you have the proper hardware to make it so that the amount of computation time that it's going to take is going to go down significantly when you're trying to do this. The other thing is size complexity, and I want to talk about this in two ways. First of all, neural networks, by and large, if you don't want your neural network to overfit, I'm not even worried about underfitting really. I'm more worried about overfitting. If you don't want it to overfit to your data set, you want to make sure that you have an extremely large representative sample of data that will be able to help your neural network learn. The danger here is that if you don't, then it'll just kind of memorize the data that you have in your training data, and it won't be able to generalize very well. The other size complexity that you have to worry about, and this is more for people who want to go work in like a tech company and start producing these models for consumer use, you need to worry about how you're going to ship those to production. Neural networks have, I think the latest neural network called GPT-3 has 3 billion parameters. They're giant. The state-of-the-art neural networks are just huge monoliths that are just crunching numbers, take tons of time to train. I don't even think, especially in like the natural language processing space, you don't even really train neural networks anymore. You do something called tuning, because training them would take so long because of the number of parameters they have, and they're so huge that it's hard to put them into production. Something that I'm seeing a lot of papers come out about now is using lighter versions of neural networks so that you can use it in a realistic way. They're super powerful, but you do have to worry about those complexity issues. For those that are outside the US, particularly in the EU, the other thing you're going to have to worry about is GDPR and the interpretability of your model. One of the bad things about neural networks, and I'm saying bad as a very specific term here, is that it'll be very hard for you to interpret what it did to learn that decision boundary, to actually figure out what it did to make that conclusion when it's making its decisions about certain data points. And we can think of certain use cases that may make us pause to have such an autonomous machine make a decision about something, particularly when, like, if human behavior is becoming huge in data science and studying human behavior. Not having an interpretable model for why someone might do something could be catastrophic for your company in terms of their bottom line, and also just in terms of an ethics sense. If you can't explain why you're labeling someone the way that you are, that's really not good. You really need to be able to explain that from an ethics standpoint, from a regulation standpoint, particularly if you're in the EU, or California has some data privacy laws that they came out with too. You're going to need to be able to interpret your models, and neural networks have a hard time of doing that. There is some advancement in the interpretability space, such as SHAP or LIME, either one of the, or Shapley, I think it's called. Either one of those do like a fine job of trying to get some interpretation, but at the end of the day, those are approximations and making guesses. It's going to be very hard for you to interpret exactly what a neural network is doing at any time. The other higher limitation that I want to talk about, and this goes to the heart of what a neural network is, and I think I brought this up when I talked about why neural networks work. At the end of the day, neural networks are curve fitting. It's a correlation. It doesn't say anything about causal reasoning. So it won't be able to learn anything. It won't be able to discern whether a task is a causal task or not. So Judea Pearl, which is one of the fathers of AI and now is one of the fathers of causal inference. If you're in a university program right now and you are taking courses and you take a course in causal inference, they'll probably bring up Judea Pearl, or at least I hope they would, because he is a godsend. And I can even send over some of his books and the resources so you can read them on causal inference. But here's a quote from him in an interview that he did. As much as I look into what's being done with deep learning, I see they're all stuck there on the level of associations, curve fitting. That sounds like sacrilege to say that all the impressive achievements of deep learning amount to just fitting a curve to data. From the point of view of the mathematical hierarchy, no matter how skillfully you manipulate the data and what you read into the data when you manipulate it, it's still a curve-fitting exercise, albeit complex and non-trivial. So the thing to take away here is that all the advancements that are going on with deep learning are still bounded by this limitation within, I'm not going to say statistics, but maybe within data science, that we're really just looking at correlations between variables more than we're looking at large swaths of being able to say this causes this, which is always going to be a larger limitation until we start figuring out how we can bring causality into our work in a speedy and efficient way, which Judea Pearl is actively working on, as well as other researchers. Any questions about the limitations of neural networks? Great. Okay, so what we didn't cover, I promised that I would talk about this because it's really, really important. How do we tune the hyperparameters of a neural network? I don't even think I got to the idea of what a hyperparameter is. But this is a really important question. You can and is something that is more of an art than a science in neural networks. And if you ever become a neural network fanatic and you are like becoming a researcher in neural networks, I promise you that a lot of your days will be used just pressing the enter button to try to get your hyperparameters completely tuned. Oh, great. These are some great questions. So is it possible to go beyond just curve fitting in this field? So I would recommend to go and read Judea Pearl's book on called The Book of Why. It gives a really layman explanation of what might go on. There is research being done to try and see whether we can go beyond just curve fitting. And there are frameworks being developed, whether it be in deep learning or in other statistical fields, to try and get at causality. What I can say is that a framework and a language has now been developed in the past half century and is starting to get popularized in the past decade, called do calculus, that allows you to at least have language to study if a causal thing is there, which is a huge advancement for the field in terms of us being able to study anything further. You can think of the same thing in the 19th century, what happened to mathematics. Mathematics before then was very loose, and big questions were really, really hard to answer that today we can kind of answer trivially. And part of that is because because mathematics adopted the language of logic and the language of axiomatics, which allowed them to move much further than where they were able to move before. Much of the mathematics even learned in school doesn't necessarily go by that framework because of the rigor that it's in. But if you were to revisit mathematics with a proper axiomatic framework, you would think about it slightly differently, but it would adopt all the same things and more than what we've studied today. Another question from Miriam, do you think that neural networks are better than conventional image analysis methods to perform feature extraction from images? I cannot say that. I am not an image, I am not someone who's done a lot of image processing work, even with neural networks. From the people that I've spoken to, data scientists I've spoken to that work in the computer vision space, they have told me that classical computer vision techniques are still used and are still operating at the same level a neural network might do, if not sometimes slightly better. But convolutional neural networks are something you might want to use just to extract features as another part of your feature space when you're building a classification model. I can say even now I'm in a data challenge where I'm doing multimodal problems, which means it has two different types of data sources, and we need to be able to feature engineer both and then feed them into a model. And one of our feature sources is an image. We're looking for ways to try and just adopt some blanket features so we can first get a first pass. And so neural networks, because the computer vision space has moved in the direction of neural networks for quite a while now, you can adopt for free just some images, some features from models for the images that you have. So that's the best answer I can give. I hope that at least gives you an inkling, Miriam. I'm sorry if it's not more satisfying. these are great questions. Are there any other ones before I move through what we haven't discussed? Great. So what we haven't discussed, how do we tune the hyperparameters of a neural network? Haven't talked about that. Like I said, if you went and became like a neural network junkie, you'd be pressing enter a lot and trying to figure out what are the exact hyperparameters. It's tedious work, but it's like something that's extremely important and can have huge gains if you find the right hyperparameters. How do we optimize a loss function? I kind of glazed over this. I talked about one technique very briefly, but if you really want to go into the optimization of loss functions and choosing the correct loss function even, you'd want to go into like something, you'd want to start studying convexity and concavity, why those two types of spaces even matter and why we even care about them, and the issues with optimizing on concave spaces as opposed to convex. And then I also briefly touched on this in a myriad of places. And I think Miriam's question goes to this really, really well. How do we know when to use a neural network for a problem? I think this is a whole other lecture, if not a course, that should be taught in universities. There are so many places, and I think there's something going around in data science that like is just false, where neural networks are this like godly thing that you should really try and strive for. Neural networks are used for very, very hard problems. They should be tried when like it seems like research, and I'm talking from the research perspective, it should be tried when research has kind of almost hit its limit. You're not seeing a lot of growth over several years. And so you want to see, can a machine learn something better than what you can? And neural networks are great for things like that. But you want to make sure that you're hitting something with a neural network when you've exhausted simpler solutions. And I said this in the beginning of the talk. You want to use a neural network when it's appropriate, not when. And as you start researching more, as you start learning more, you'll start getting this kind of art of when you should start considering using a neural net and when you should start considering using other classical or new machine learning algorithms that are coming out. I think this is what I'm saying is a little controversial. I know some people who are like, let's just use a neural net for everything, because honestly, you can. There's nothing inherently wrong with that. But you're missing out on like the art and the science behind data science, in my opinion. And I think the other side of the argument, if you're just hitting everything with a neural network. Happy to talk more about that at the end if people have questions. Types of neural networks that I did not discuss. There are many of them out there. Some that have come across my purview. Transformers. If you want to learn more about transformers, again, the natural language processing talk will go into a little bit about transformers. We will not go super deep into it, kind of like the same high-level overview we did here, but we will at least get the intuition behind them and what is kind of going on, so we can understand this extremely powerful tool that's come out in the last couple of years. GANs, generative adversarial networks, didn't talk about those. There's something called a Siamese network. One of my friends introduced me to just recently, like I think less than a month ago. Recurrent convolutional neural networks are another one, and many more. And again, this goes to the science of neural networks. This is like right now for data science, if you're going to start using neural networks, it's like the Wild West. There are no best practices. There are very few best practices in terms of using neural networks. Every field has neural networks that they like using because of the type of problem that they're using, and new architectures and new ways of thinking about a neural network are always coming out to try and solve new problems that are going on, or not even new problems, just someone figured out something and now it applies. Some resources, and I'll have a larger list of resources in the email that I send with this deck. 3 Blue, 1 Brown. I can't emphasize this enough. He has an amazing series on linear algebra, on calculus, and on neural networks. Again, it's not going to go super in depth on any of those topics. I think it goes deeper on the deepest on linear algebra. So if you really need a refresher on linear algebra and you've taken the course before, it is fantastic. If you haven't taken the course before, this will give you an intuition that very few classes will. And the same thing with all of his talks. It's just he's really good at breaking down what's going on without getting stuck in the mathematics. Towards Data Science is a great blog that people use on Medium. They have some great articles if you want to learn more about data science in general, or if you want to learn about cutting edge neural networks. They have a plethora of people posting every single day. And they're usually really good because they're like down to earth layman, like they focus on implementation more than theory most of the time. So if you want to learn about that type of stuff, Toward Data Science is great. I do want to I do want to talk about two books. They're both free. You can go find them online for free. One is called Dive into Deep Learning. I think this is a project out of MIT. If I'm citing that incorrectly, I'm really sorry, authors of Diving into Deep Learning. What's so powerful about them is that they continuously are updating this book. So you can just keep on going. They just added stuff on transformers. They just added stuff on some cutting edge NLP stuff. But it's just a very comprehensive book. And they also have Jupyter notebooks attached where you can go look at code and you can play around and have exercise answers and stuff like that. And it's also very well written. The linear regression example that I had for this lecture comes from that book. Neural networks and deep learning. This is the first book where I read about the universal approximation theorem. It's a great read and it's very interactive. It's not like the Dive into Deep Learning book where they have notebooks, but instead they have like embedded videos and interactive images that you can really just start playing with parameters and start seeing how things are working in real time. They don't have as many exercises as Dive into Deep Learning, but if you need something that's really like down to earth speak and very, not lay, but just very concrete, and isn't worried about too much about implementation, but is focusing a little bit on theory. Neural networks and deep learning is a fantastic read. And then in terms of like, if you really want to just get to the nuts and bolts, you're like, Daniel, I don't care about why any of this is working. I just want to be able to code up a neural network and make 1 million layers and just see what happens. PyTorch, TensorFlow, etc. There are other deep learning frameworks. Their documentation's fantastic. Most of them have a tutorial section where you can go read up on implementation of code. And they include most of the time a lot of the advances that are going on in the deep learning community in most fields. They might be behind a few years, but it'll only be a few years. And they're fantastic frameworks. I personally use PyTorch all the time as my preference. A lot of people like TensorFlow more, but either one is great. And there are other ones that you can go and research too. And with that, thank you all so much for sitting through me talking about neural networks for an hour and 15 minutes. Any question? My email's here. If you guys want to email me, of course, I'm going to email you back, email you out. But if you have any questions before I send my email out, here's my email. And if you have any questions now, like feel free to share in the chat.
And I think also you can now unmute yourself if you have a question and you would like to say it.
Yeah, that would be great too.
So, hello.
Hi.
Hi. First, my name is Jose. You
Jose,
didn't know.
thank you so much.
Spell it.
Yeah.
Yes. I have a question. I don't know. I am a newbie to this stuff about artificial intelligence, and so I've only taken the crash course by Google, and I have some big ideas, but it isn't like really concrete for me. I don't know what happens. So data science and all the stuff is kind of software stuff or hardware, or how is it implemented actually?
Oh, that's a great question. I would say it's a combination of both. So from the software perspective, you need the languages that are most supported for, like, if you're talking just general data science, Python's extremely popular. I'm sure you learned that from your Google course. Something that's increasing in popularity, if you're worried about like time complexity type stuff, like you're worried about speed, because Python's a high level programming language, which means it doesn't interact directly with the hardware in your computer. It has to go through an interpreter phase. You might want to look into Go, which is a low-level programming language that Google came out with. I personally want to go learn Go just because it's a low-level language that you can use to start doing some ML stuff. I'm not sure if deep learning is as supported or as easily supported in Go. I can't say that, but in terms of ML, I've read articles about entire businesses using Go as their only language for machine learning. They don't even use Python in production. Julia is another programming language in terms of software for you to learn, which is becoming increasingly popular for data science use. And of course, R, MATLAB, etc., are all popular languages to learn. So it's both a software issue. So it's, you know, there are algorithms that need to be thought of and implemented in terms of some language to then get interpreted by the computer to then solve some type of problem. But then it's also a hardware issue. So from the Google course, I'm wondering if they talked about TPUs, which are, I think they stand for tensor processor units. And the hardware issue is figuring out the space requirements and figuring out new processors that can handle the number of computations that are happening. So the time complexity, for example, from neural networks, like I was talking about in this talk, it doesn't come from the fact that the algorithm itself takes a lot of time to run, right? Like if you put one training example in there, it probably wouldn't take any time to run. The issue is because the amount of data you're putting in. So it's the number of computations that you have to do that blows up the time complexity. So you need to come up with hardware that is going to be able to do those computations very efficiently so that you can handle those huge amounts of data. And then when you're handling huge amounts of data, you then need to think, okay, we need to have like either tons of servers that are going to distribute the work. That's where like distributed processing comes from, or cloud services. Or you're going to just have one computer that's massive. Like that, like this is where like Mac's like $50,000 computer that they're selling to consumers. I bet you there's some programmer out there who bought it because they're like, now I can just do stuff on my computer and it'll work fine. So you need to worry about all of those things from a hardware perspective. I'd say a lot of the innovation, I actually don't want to say that. The innovation is in both the hardware and the software. Like I'm more privy to the software stuff because I don't consider myself a software engineer or someone who does hardware stuff. I'm a data scientist, and most data scientists I know are more concerned about like the implementation in terms of software, and we'll just use whatever out of the box hardware we can get our hands on, whether it's some cloud instance or whether it's our computer, as long as it can do the work that's required for the task. But there's innovation in both sectors that's going on to try both to make the hardware better and then also make the software better. I hope that answered your question, Josie.
Yeah, that's fine. Can I ask like a little thing just to make things like clear in my mind?
Mm-hmm.
About training. Okay,
Yeah.
so it's a matter of giving inputs and observing the outputs and checking if they are similar to what I expect.
Mm-hmm.
But actually, when they show us training, like something lines going up and down, and this process,
Mm-hmm.
what actually happens inside the calculation?
Yeah.
Is it what happens? What is training? What happens?
Yeah, so Wedad told me that I should have like a notebook up, and I think this is a great question to show some code. I don't know which one I want to use. I'll go with PyTorch's learning example. So here is some code that someone might write up. Here's like the layers that they would have for their neural network here in their init for their class. And then their function would be forward, and this is where usually you would put like your activation functions for your neural networks. As you can see here, they're using ReLU. I think it's because of the clamp. They're using like different functions than I usually use, but then you have your dimension sizes. That's for initializing your neural network. And then you're talking about training. In the training step, it's like a little bit black boxy. So you'll have some type of loss function, some type of function to measure your loss. Just like you said, you're going to have some comparison between your output and your input. That'll do some type of calculation. And then you'll use something, the bread and butter for you to first try is like stochastic gradient descent, which is a randomized process for doing your gradient descent. And I think this, the optimizer that you're choosing, the thing that's going to be doing the whole gradient updates, that is going to be the thing that's going to possibly perturb your differences. So you're saying something like where at one moment when you train, it goes really low and then it jumps back up, right? Something like that. Yes, no?
I don't get your point. What is this? Going down and up? I don't know.
I'm just trying to understand what you were saying. So you're asking what happens like in training, right?
Right.
Sorry, could you type it in the chat? You're breaking up a bit. I just want to get the exact question so I know what I'm answering. Yeah, so it's just calculations. Yeah. If it's that simple of a question, so you have some type of loss function that's going to do a comparison between your output and what your input label was. That loss function is then going to be used as to update whatever's going on. And then the gradient descent is going to be your optimizer that's going to help point the derivative in the right direction based on whatever your outputs were. This is a very simplistic way of talking about it, but yes, it's a bunch of calculations in terms of comparing input and output to try and find what is the best direction for the rest of the parameters to update to get a better loss in the next step. Now, I do have my own code here, and I can show how it looks. And I'm trying to see, are there any examples where it like jumps up? Because something with neural networks is that they don't always go straight down. They'll jump back up every once in a while because it's not perfect how they are finding the decision boundary. I think this one might have just kept going down because I optimized it really well. Yeah, I think this one kept going down. But in practice, like if you look at these numbers, you might go from like 0.00061 to like 0.0059, and then it'll jump back up to like 0.0065. And that's not like unexpected or anything like that. It's just part of the training. And again, this is all art. This is not science. Like it's kind of like you kind of make a decision on that. You have some other metrics that you might want to measure to validate whether you're overfitting or not, etc. So yeah, it's really just doing a bunch of calculations on your neural network and just trying to figure out your error and optimize for a lesser error. Cool. Any other questions? That was a great one. Cool. I'm getting a lot of thank yous. So I'm guessing I'm guessing there are no other questions. it was great talking about this stuff with you. I hope you learned something. I'm still learning about neural networks every single day. Whether I'm reading a paper, talking to a friend, again, it's the Wild West right now. So just go read research. I'll send some things so you can get started in terms of getting some intuition. I highly recommend, if you haven't already, take a linear algebra class, take a calculus class, take a multivariable calculus class, learn some probability. All of those are the bread and butter of data scientists, and having a good foundation in even just one of those is going to elevate the amount that you can understand of what's going on, both in neural networks and in general data science. But particularly for neural networks, try and learn some linear algebra and some calculus, and you could really just go and read any paper from there, as long as you're willing to trudge through the jargon that data scientists love to use. So thank you guys so much for being here for this presentation. I hope you learned a lot. And with that, I'll let you close out if you want.
Thank you, Danielle, for this workshop. For me, like, it was useful. I am also like, I think for all who attended also it was useful. If I can say from the thank you comments.
Yeah.
So Danielle will send you the slides and the like recommendations, what you should do, what's better to read, or and maybe courses. I'm not sure.
Yeah, sure. I can. I'm gonna try and make sure that whatever resources I choose are free. So I'll do my best to find some free deep learning courses, but primarily I'm gonna send books, videos, blogs, etc.
And also, Danielle will share with you the recording. So Danielle, I will send you the recording.
Okay, great.
So thank you guys for attending, and I hope you will have a nice weekend and the rest of Saturday in case you are morning or afternoon for a few hours.
Yeah, have a great one, everyone. It was a pleasure and a privilege. Have a great day.